And we created a couple of directories and a couple of test files. So we have this simple structure: 2 empty directories and a file. Now, first we will start with hard links. We can use the command ln, which is short for link. Link this file to fun hard. Hard is for hard link. And also I can make another link to the directory dir1 and also to the directory dir2. And if I see the structure, now I have these files which are hard links to this one. With this command, this is for recursive, list long and recursive. We can also see the content of directories and subdirectories. And if I also have this option I to the command ls, it is showing an additional column, which is this one here. And this is for inode. It is the address where the content of the file is starting. And if you check here, all these files have the same address. So the content of the file is the same. So a hard link is like another name for the same file. If we think of a file like a box, and the content of the file is inside the box, and the name of the file is a label on top of the box, when we create a hard link, we just place another name on the box, but the content of the box is the same. So there is a box with, in our case, there is 1, 2, 3, 4 different names. So if I open this file and modify it, and I check this file, the content of this file, I will see that it has been modified as well, because it is the same content, actually. So this is the hard link. So we use the command ln, link, to create a hard link. Another type of link is a symbolic link. Let me create a symbolic link. We use the option -s to create a symbolic link. And if I list now this file that I created, the long listing is showing that this is a symbolic link to this file. Now, what is the difference between this hard link and the symbolic link? This symbolic link is like another box which contains inside the address to the other file. So this one and this one are the same box, but there are 2 different names on the same box. But this one is a different box, a small box, and the content of this box is the address of the other box. So it is the name of the other box. So it is like a pointer to another file. Let's create some more symbolic links. lns. This is the address that will be saved inside the symbolic link, and the name of the symbolic link or the file is and another one. And let's check the content of the directory. Now I created this one here and this one here. And the content of this file is the address of the other file, which is /fun. Dot is the directory above, which is the root, this home directory that we are using right now. So this is a relative path to the other file. And also here it is the relative path to the other file. We can also use an absolute path to link to another file. For example, link symbolic So this is the file that will be created, and the address inside this file is that will be stored inside this file is this one. This is an absolute path. It is starting from the root. Home user1 is the home directory of user1 is the home directory of user1, and then we are inside the directory test1, and this is the name of the file inside this directory. So I am telling the system to create this file, which contains inside the name of another file, which is an absolute path to the other file. But look what is happening now. It is failing to create the symbolic link because it already exists. In order to override it, I can use the option F. F is force. So if I use the option F, if the file already exists, it is going to remove it and create a new file. So here is the new symbolic link. It is pointing to home user1 test1 fun, which is the file here. We can use a symbolic link to another directory. So this is a symbolic link to a file, but we can create a symbolic link to a directory as well. For example, ln-s. This is the name of the directory. So we have this file which contains the name of a directory inside. So it is a symbolic link to this directory, which is this one. So if I list this directory, ls dir1 sim, I will see the same content as this one. So because this is a symbolic link to this directory. Now, what is the difference between a hard link and a symbolic link? Why do we need symbolic links? Because there are some things that cannot be done with hard links. For example, with hard links, we cannot link to a directory because it is just a name to a file, another name to the same file, but this does not work for directories. But with symbolic links, we can link to another directory. And also, if there are different partitions, disk partitions, with hard link, we cannot link to a file that is in another partition. But with a symbolic link, we can also link to a file that is in another partition. So both of them are useful. In some cases, one of them might be more useful. Now we can use the command. Yes, Thomas.
So if I understood well, so the symbolic link is just a pointer.
Yes.
And in fact, if I see the size is really, really small, but the hard link is like a copy of the same file. But if I modify one, it modify all the others.
Yes, that's right. Also, if you try to modify a symbolic link, you actually will modify the other file that is pointed to the symbolic link.
And also in hard links.
Also with hard links, if you modify a hard link, it will modify the content of the original file, because actually there are not different they don't have different contents. It is the same content with two different names. If I say edit this name, the file with this name, it will edit the content of this file. If I say edit with this other name, it will again edit the same content, because it is the same file with two different names. It has two different names with hard links. But with symbolic links, we have the address of the other file in the symbolic link. So if I say edit this symbolic link, actually it is going to edit the file where the symbolic link is pointing to. the operating system knows that this is a symbolic link and there is nothing to be edited inside this file, but it goes and edits the file that is pointed by this symbolic link.
Okay.
And we can see the difference between them, for example, if we remove a file. So let me show again the structure of the directory. Now, if I move a hard link, nothing happens because I just remove a name. For example, let me remove this one. With command rm is remove. Now, if I show the tree, nothing special happens. I just removed one name. It already has 4 names. Now it has 3 names because I removed one name. But if I, or for example, let me remove this one, the original file. Now see, this one, the hard link is still unchanged. So I can still work with it. I can edit the file, but all the symbolic links are broken because all of them were pointing to a file that does not exist anymore. So this red color means that the symbolic link is broken. The destination file does not exist anymore. So if I try to edit this one, for example, nano fun sim, it is empty. There is nothing inside. It does not exist. It is like just nano. But if I try to edit, for example, this one, dear one, fun hard, you see that it still is the same, the original file, unmodified. I mean, I removed the original file fun. I removed this file, but this one I can still access the same file with the different name. I just removed one of the names of the file. I'm not sure if I made it clear, but anyway, let's continue.
Yeah, thank you.
Okay.
Thank you.
You're welcome. And now we can use the command remove to remove the other files and directories. For example, if I want to remove the directory dir1, I can use rm dir1, but it is refusing because it says it is a directory. In case of a directory, I have to use the option -r, which means recursive. So if I say remove -r recursive directory 1, it is going to remove the content of the directory 1 first and then the directory itself. And it is going to do this recursively. If it has some subdirectory, then it is going to remove the content of the subdirectories first and then subdirectories themselves, and then remove the content of the directory and then remove the directory itself. So this one is directory 1 is removed. And now I want to remove this directory test1. I go one directory above, which is the parent directory, and remove recursive test1. And it is gone. Now we will see another section which is about the ownership and permissions of the files. But first let us create a test file. I can create an empty file with the command touch. So this is just an empty file. The command touch creates an empty file, and we see that the size of the file is 0. There is nothing inside the file. But we see that there are some columns. The first column are the permissions of the file. This column is the owner of the file, and this one is the group of the file. And then this is the date of creation, modification, etc., and the name of the file. So each file in Linux has an owner. So if the user 1 creates the file, then the file belongs to the user that created this file. And also each user belongs to a default group in Linux. And the default group for user 1 is user 1, again, the same name. A user can belong to different groups, and a group can have different users, but when I create a user, for example, automatically it creates also a group, a default group for this user. And so these permissions show what can the user do with this file, what can the group do with this file, and what can the other users of the system do. So these three permissions are the permissions of the owner. And this is read-write, and it can be also an X here, which means execute. And these three letters are for the permissions of the group, and they can be R, W, and X, read-write and execute. And the last three permissions are for the rest of the users, all the other users of the system. So the owner of the file can read and write the file, but cannot execute it. It is not an executable file. And also the members of this group, it can be another group with other users, all the members of the group can do read-write but not execute, and all the other users of the system can just read the content of the file but not modify it, not write, and it is not an executable file. They cannot execute it. Now we can use the command change mode to change the permissions of the file. The permissions are this one here. For example, change mode 600 foo.text. Now, what does this 6 mean? Okay. Can you please make the dark blue color of the folders more brighter? It is very hard to read on the black background. I will try on the next session, Andreas, because I'm not sure how to do it right now. But for the next time, I will try to, or let me see if I can do it right now. Is this more readable? Is this better? Or?
For me, it's much better.
Okay. Usually, the black background is easier for the eye. It does not. If you stay for a long time, your eyes do not get tired. But anyway, if this is more readable, let's keep it like this. Let's keep it like this. Okay. So what does this 6 means? This 6 is an octal number. So there are binary numbers, hexadecimal numbers, and also octal numbers. Numbers with base 8. So an octal number 6, 6 means 1 1. So this 6 in binary means 1 1 1. So it is expressed in binary like this. Not 1 1 1. It is 1 1 0, because this means 4, this means 2, and this means 1. So 4 plus 2, 6. So this 1 1 0 means that we are giving the read and write permissions, but not the execute permission for the owner. And the second number, 0, in binary is written like 0 0 0, and also the other one is 0 0 0. The third 0. So this is why it is giving these permissions. So read and write permission for the owner, but no permission for the group and no permission for the other users. If you don't know how to work with binary numbers, and if you don't understand this, then there is an easier way to assign or to modify permissions. Change mode, user plus X, okay, I made the font bigger. So change mode, user plus X. It is meaning the it means that to the owner or the user add the X permission. So it is adding the X permission to the user or to the owner. And I can also remove a permission with minus. So u minus X, it means remove the permission X from the user or the owner. I can also do something like this. So user plus X, comma, then group and others equal read and X. So it is adding the X permission for the user, and for the group and for the others, it is setting the permissions to read and execute, which is this one: read, read and execute. Or I can do something like this: change mode, user group others minus X. What does this mean? It means that remove the X permission from user, from the group, and from the others. And we see that the X permission is removed from all of these three groups. And if we have to remove or to add some permission to, instead of this UGO, we can also use A, which means all. So if I say all plus X, it is adding the X permission to all of them, to all three of them. And instead of all, I can just use plus X, which means add the X permission to all three group of permissions, or minus X, which means remove the X permission from the owner, the group, and the others. So this way of managing the permissions is more user-friendly, I think. But also something like this once you get used to it, it is also very convenient and faster. Now let's see something about the processes. Let me clear the screen. And we have this command ps to show a list of processes. And it is showing the processes only for this shell, for this terminal. But if I add the option A, it is giving the all the processes, and if I also add the option U, it gives all the processes for all the users, I think it is displaying also the user. It is displaying also the user in this column, and also some other columns. CPU percentage, memory percentage, etc. This TTY is the terminal from where the process has been started. This bash is the process of this shell that we are running in the terminal. And this is the command ps itself. So the ps itself is also listed in the output of the command. And in this case, TTY1 is the terminal. So here we see, for example, that this process is started by the user root, but these two other processes are started by the user one. And with the option help, we can see some we can see how to use this command. And actually, we can see the simple options. List, output, threads, etc. Or we can see all the options of this command. So let's try to see the simple options. So there is this option -a and the option a. They are similar but different. And usually the options in a Linux command start with this minus, or with this double minus and then a long option, or minus and one letter. But because this process is an old command, it also recognizes some strange options like this one, without that don't start with dash or with minus. So the processes that we have listed above are processes with TTY that are started from the user, from the shell, from the terminal. But if we use this option X, we can list all the processes in the system without controlling terminal. So the programs that are running in the system, even if they are not started from a command. So let's add this option X to the command process, and actually it is a very long list. I can pass the output of this command through the pipe to the command less, and it is going to show it with pages. So this is the first page, and then I press space. Next page, space. There are a lot of processes, actually. All the processes that are running in this system. And I exit with Q, or quit with Q from the command less. We have seen the command last time as well. It is showing the content of a file, but in this case, it is getting the data from the standard input through this pipe. So the output of this command through this pipe is going as input. It is forwarded as input to this other command. So let us run it again, and we see that the first process has this PID, process ID number 1. This is the initial process of the Linux system, and all the other processes are started from this one. Because okay, let me show another command. Quit from this, and let me use the command ps3. So there is also this command ps3, which shows the list of processes like a tree. So there is one process at the root of this tree, and it is starting this process. This process is starting 3 other processes, and this one is starting this one, and this process is starting 3 other processes, and so on. So each program that is running, is the process, but it is started from another command, from another process. If I type a command at the terminal, the parent of this process is the terminal, the process of the terminal, or the shell, the process of the shell. So they have this parent-child relationship. Each process has has a parent and has some children. For example, this process has one parent and 3 children, except for the initial process that was this one. That was this. Okay, it is not displayed very well here. Okay, anyway, which is the initial process of the system. Now I can call the process PS3 with the option -p, which is going to show also the process ID for each process, because in this list we see just the name of the process but not the ID of the process. And also we can pipe it to the command less. So this is process number 1, and then each process has some number, and it is starting some other processes, and so on. If I give a username, for example, user1 is the name of the current user, it is going to show all the processes of this user. Let me pipe it to the command less. So this is the graphical interface of Raspberry Pi XYLand. All of these processes belong to this user, user1. Another command is the command top, and this shows a list of processes, but this is a dynamic list of processes. It is refreshed every 2 or 3 seconds. So the second part here is a list of processes, but they are ordered according to the resources that they are taking. How much CPU is using one process and how much memory. So the most the process that is consuming the most resources right now is this program, which is the recorder, which is recording the screen, my screen. And the other process is the browser, Chromium, and so on. This is the graphic interface of Raspberry Pi, and so on. This is a summary of processes. This up 52 minutes shows that this system has been running for 52 minutes. There is one user currently in this system, and load average. These tasks are the processes and threads in Linux are called tasks. So when we see tasks, it includes both processes and threads or threads. I don't know how it is pronounced correctly. So one program can have several threads, which are parts of the program running in parallel, and they are considered the same as processes in Linux. So they are called tasks. Both processes and threads are called tasks. There are 230 tasks. There are only 2 running, and this much sleeping, and so on. And this is the percentage of CPU that is being used by the user, by the system, and so on. Anyway, I can stop this command by pressing Q. Now I will use this command sleep 100, which is going to wait for 100 seconds. And now this command is running, but until it is finished, I do not get this prompt. I can press Ctrl C to cancel the program, the command that is running. If I want to run this command in background, I can append this ampersand, this character ampersand, and this will make this command to run in the background, and I will immediately get the prompt to give another command, the prompt of the shell, so that I can insert another command. And if I check the processes, I will see this process as well, sleep here, which is still running in the background. And if I want to stop this process, I can use the command kill -9 and then the process ID. Now in the list of processes, I don't see anymore this command, and there is this message that this process has been killed. There is also another command that is named kill all. Let's see an example with this one. I am starting this process in the background, sleep 100, and then another process, sleep 200, and then another one, sleep 300 seconds. If I check with PS, I see that there are 3 processes that are running in the background, and also with the command jobs, I can list all the processes running in the background. Jobs are processes that are running in the background. And now I can use kill all sleep. It is going to stop all the processes that have sleep in their command. So I see these messages, terminated, etc. And if I check with PS, there are all of them have been stopped. Also with I can check with jobs. There are no jobs listed. So the command kill takes a process ID and a signal. It is actually sending this signal 9 to the process ID. For example, to this one, although it does not exist anymore because it has been killed. With the command kill, I am sending this signal to the process, but with the command kill all, I am giving it a name, and then it is going to stop all the processes that contain this word in their command, in the command that started the process. Now let's see something about redirecting and pipelines. Let me list the content of the directory user bin, and I will store the content, the output of this command to. I can store the output of this command to the file Now, when I run this command, nothing is displayed on the screen. Why? Because the output of this command is forwarded to this file. It is this file here, and I can check the content of this file with the command ls. So it is the output from the ls command that we tried before. I can list the content So with this command, I'm making a long listing, but this option H is also showing the size of the file in human readable format. So this file is 133 kilobytes. Now I will call the command before, but instead of one redirection or this greater sign, I'm going to use double, two of them, and see the content of the file again. Now the content of the file has been increased because this operator is appending the output of this command to this file. This redirection operator is deleting the file on the right, is creating a new one, and then saving to this file the content of the command that is on the left. But this operator is not deleting the content of the file, but it is appending to this one, and that's why the size of the file is increased. Let me try it again and check the content, the size of the file. We see that the size still again is increased because we are appending. But if I try with a single greater sign, check the size of the file, we see that it has removed this file, and it has forwarded the output of this command to an empty file. So it removes first this file, creates a new one, and then executes this command, and the output of the command is saved to this file. So this is redirecting the standard output of this command. Each command in Linux gets some input and may generate some output. The input is received from the standard input, and the output is sent by default to the standard output. The standard output is the screen, usually, the terminal. And the standard input usually is the keyboard. So a command usually gets an input from the keyboard and then outputs to the screen. But we can redirect the standard output. In this case, we are redirecting the standard output to a file, so that the output of the command is not being sent to the screen, but it is saved to this file. And if a command produces some a command may also produce some error messages, and error messages usually are sent to the standard error, and the standard error usually is the screen again. So if there is an error message, it is displayed on the screen. But we can also redirect error messages, or we can redirect the standard error to a file. And we can redirect both the standard output and the standard error to a file. So let's see this command, ls -l. This directory actually does not exist. This one exists, /usr/bin. /bin/usr does not exist. So this command is producing an error message. ls cannot access no such file or directory. Now, if I use this one, this redirector 2 and a greater sign, it is going to redirect the standard error to a file. So we see no error message in the screen, but if we check the content of this file, we see that it contains the error message. And we can redirect both the standard error and the standard output with this operator. So this @ and greater redirects both the error messages and the output messages to this file, both of them. And if we want to append, we can use this operator. So @ and then @ and then this double greater. So if I run it a couple of times and check the content of this file, I see that all the error messages have been appended one after another. Yeah. And if we don't care about the error messages of a command, then we can redirect error messages to dev null. Dev null means destroy the message. It is not saved anywhere. So if there is an error message, we send it to dev null. We just destroy the error message because we don't care about it and we don't want it to be displayed on the screen. So we redirect it to this special file, this special file /dev/null, or a special device. So we have seen the pipelines. The pipeline is an operator that gets the output from one command and sends it as input to another command. We have used it already, but let's see another example. ls bin, and then we will list also this directory. So we are listing the content of this directory and the content of this directory. And now we can pipe it to the command less so that it is displayed page by page. Q to exit from this command. And instead of the command less, we can use the command, this is a word count. It is counting the number of words in the input. But with the option -L, actually it counts the lines. So there are 4,279 lines in the output of this command. We can pipe the output of this command to the command sort, which is going to sort the output of the command, and then we pipe it to the command less. So we are building a chain of commands. One command sends the output to another command, and then the output of this command is sent to another command, and so on. So we see that it is sorted. First start the lines with A, and then the lines with B, the lines with C, and so on. And before after sorting them, we can also pass the output to the unique command and then to the command less. This unique, in case there are 2 or 3 lines that are identical, it is going to keep only one of them. So it keeps unique lines in the output. And if we count, for example, how many unique lines are, we can count with this. There are 2,000 unique lines. So some of the lines are repeated. There are lots of lines that are repeated in the output of this command. And with unique, we are reducing the number of lines to this number. And this command unique can also be used. This command sort also actually has an option that does the same thing as the command unique does. For example, not for example, but if we use this option -u, this option -u of command sort does the same job that unique does. So it removes the duplicated lines and keeps just a unique line. So we see that the output is the same. And we can use the command grep, for example. So we produce some output with a chain of commands, and then we pass it to the command grep to search for the lines that contain a word or a regular expression. So it is listing all the lines that contain this word. In this case, it can be a regular expression. We don't have time to explain regular expressions right now, but it can also be just a simple word like this. And if we want to count how many lines are displayed above, we can use this one. There are 21 lines that contain the word zip. Let's see also these head and tail commands. But first, let's make sure that we have a file with some content. So we have this file, and now if I use head, it is going to show the top 10 lines from this file. So head means the lines on the top of this file, and by default it shows only 10. But if I give an option, for example -n5, then it is going to show only the 5 top lines. And similar to the command head, we can use the command tail. And tail shows the lines from the bottom of the file. And I am telling it to show 5 lines from the bottom, but by default it shows 10 lines on the bottom. And I can also give the option, the number of lines like this. For example, -5. And it is going to show just 5 lines from the bottom of the file. And we can also use the option -f, which means follow. The option -f is displaying the last lines from the file, but it is still waiting in case some more lines are added to the file. This is useful in case we check log files. We will see examples during the course. We will use some commands like this, where we check the logs of one service. Ctrl-C or Ctrl-D. And let's see also shell expansions and quotes, a couple of examples, and we will stop for today. Now, I'm using this command echo. First of all, the command echo gets some arguments, and it is displaying to the output, to the standard output, all the arguments that it reads from the command line with a space in between. So it is getting this one as an argument, this one, and this one, and it is displaying these arguments with a space in between. Now we see that we have here lots of empty spaces, but this command is ignoring these empty spaces. Actually, it is not the command that is ignoring the empty spaces. When I type a command to the prompt, this is the prompt of the shell. I'm typing this command to the prompt, and then I press enter, which means I'm telling the shell, get the command and interpret and execute it. The shell, which is the bash, in our case, we are using bash, the shell is getting this input when I press enter, and it is interpreting it like this. First of all, it is splitting it by empty spaces. So this is also a splitter. There are all empty spaces. And it is getting this word, this word, this word, this one, and this one. It is going to interpret the first word as the name of the command. And it is going to search for this command. If it finds this command, then it is going to execute this command, and it is going to pass the other words as arguments to this command. So this interpretation is done by the shell. And the command echo itself just gets these arguments, and what it does, it displays the arguments that it receives. Now let's try this example, this other example. Now I'm using these double quotes. I'm enclosing all this in double quotes. Now we see that the space is preserved here in the output. What is going on? What is happening? Why this is different from this one? This is different because when the shell interprets this command, because of these double quotes, it is taking all of this as a single argument, and it is passing this argument to the command echo, and the command echo is just displaying the argument, but the argument contains these empty spaces inside, so we get empty spaces in the output. So in this case, the command echo is getting 4 arguments. In this case, it is getting just 1 argument because of the double quotes. So this is one of the functions of double quotes. If some arguments contain spaces, empty spaces, we can enclose these arguments in double quotes to preserve these empty spaces. Otherwise, the shell will interpret these empty spaces as separators between arguments. Now, let's see an example with shell expansions. So when a shell interprets the command, it can also do some other things. So this command is going to demonstrate what are these things that it does. Just a couple of minutes and we will stop. So please be patient. And I'm going to explain what each of these commands means, these arguments. So when the shell looks at these curly braces, it is going to interpret this as a list of options. So it has the option A and then comma the option B, and it is going to pass these 2 options as arguments to the command. So the command echo is printing, is displaying these A and B arguments. Now when it is seeing this $sign and this parenthesis, then it is going to interpret the thing inside the parenthesis as a command. It is going to execute this command and take the output from this command and send it as an argument to the command echo. So the shell executes this command, and the output of the command is this one. And this is what is sent as an argument to this command. Now, this is an environment variable. So it starts with $, and a name. The shell tries to interpret it as an environment variable and tries to get the value of this variable. And actually, there is such a variable in the environment, and it contains the home directory of the current user, which is this one, /home/user1. So this is replaced by the shell before this command is executed with the value of the home directory. Now, with this $sign and double parentheses, the thing inside the double parentheses is interpreted by the shell as an arithmetic expression. The shell evaluates this arithmetic expression, and the result of the evaluation is being sent as an argument to this command. And the result is this one, this number, 4. And here we have a range. This 1 and then dot dot 5 is a range from 1 to 5. The shell is interpreting this one as a range, and it is replacing it with the numbers 1, 2, 3, 4, 5, which are being sent as arguments to the command. And now this is again replaced with something else by the shell, or it is expanded. This is the terminology that is used in Linux and in Bash. That's why these are called shell expansions. So shell is replacing this one with something else. It is looking, it is trying to match all the file names. So because of this wildcard, it tries to match all the file names that match with this expression. And the file names that match this expression are this one, foo.txt and lsoutput.txt. And these are sent as argument to the command echo, and it is displaying them to the standard output, which is the terminal. Now I will run the same command as before, but I'm going to enclose all this with double quotes. And now see what happens. These double quotes disable this curly brace expansion. So now this is not replaced by the shell with A and B. It is treated as an argument. It also disables this one. Again, we have this. And also this disables this expansion. So we don't have the names of the files here that match this expression. But these double quotes do not disable all the expansions that start with a $sign. So still we have here the output of the command, we have the value of the variable here, and we have the value of the arithmetic expression here. So these double quotes disable some shell expansions, prevent them, but not those that start with a $. Now let's try the same command again, but with single quotes. Now we see that these single quotes disable also the shell expansions that start with a $, so nothing is expanded. All of this is treated as an argument. So this is the argument that is passed to the command echo, and this is what is being displayed exactly. So if we want to disable all shell expansions, we can enclose it with single quotes. Now another, the last example. Now first of all, the command cal displays this calendar of the current month. But when I run this command, this is a shell expansion. The shell runs this command and takes the output of the command. This is the output of the command, and it is replacing this with the output of the command. But there are some empty spaces in the output of the command, but all of them are ignored, and it is sending this one as argument, this one as argument, this one as argument, and so we have we lose the formatting of the output of the command. Now let's try this command with double quotes. With double quotes, the shell expansion again is done, because double quotes do not prevent a shell expansion if it starts with a $. But because we are using these double quotes, all of this is interpreted as a single argument, and the spaces are preserved. So the output is formatted, the output from this command. Now, if we use this single quotes, Now, these single quotes prevent this expansion of this executing this command and taking the output of the command as an argument. So this is displayed instead, exactly what we write here in single quotes.